Welcome back. So I wanted to get at least into what exponential functions look like in terms of equations. All right, so exponential models examine growth or decay where the variable is an exponent for a common base. Right, so our variable here is always going to be an exponent. As such, the growth or decay occurs as an increasing or decreasing pattern of a constant base raised to an ever increasing or decreasing power. So you have this in your notes, the equation for exponential functions. So an exponential function has the form f of x equals a times b to the x, where a is not 0. You can't, if you start off with nothing, no matter how much time goes by, it's still going to be nothing. Your base can't be 1, because if you raise 1 to a power, you're just not going to change. It's still going to be 1. Like 1 to the 10 millionth power is still 1. And your base has to be positive. Right? So let's look at why these things are true. And I'm going to have you fill in your notes. All right? And I have no idea what this little blip there is. Maybe it's pointing out my 1. I think that's what it was. So in your notes under, it's like the first thing it says the base cannot be blank because blank. Right? So fill in the base cannot be 1 because 1 raised to any power would be 1. Right? That wouldn't be growth at all. That would be a constant function. It would never change. The second thing your base can't be is 0. So fill in your notes on the second blank there. The base cannot be 0. Right? And the reason it cannot be 0 is over here. So my reason is not necessarily right next to my thing. So right next to the 2 here, you see that division by 0 is undefined. Right? So that would be what you'd put next to the because. So for instance, if I had 0 as my base and I raised 0 to the negative 1 power, I would get 1 over 0. And that's not defined. That has no meaning whatsoever. Right? So that's why 0 cannot be our base. And then lastly, we can't have negative numbers. Right? So our base cannot be negative. Right? Our exponent can be negative, but not our base. Right, so on the third blank there, you're going to write negative numbers. And then the reason why is because they would not be real numbers or would be undefined. For instance, if I had negative 16 and I raise that to the 1/2 power, that's the same as the square root of negative 16, which we know is a complex number. That would be 4i. Right? Well, we are not dealing with complex numbers in exponential functions, right? So that has absolutely no meaning for an exponential function. So our base is not going to be a negative number, right? So we looked at what our base can't be. Let's take a look at some more things about exponential equations. And our base can be anything else, just can't be 0, 1, or negative. Oops, I accidentally hit the wrong thing. So here we have a table and a graph showing an insect population that increases over time. All right, so in the beginning there are 2 fruit flies. Right? We have to start off with something. If there are no fruit flies, 10 days later there will still be no fruit flies. Right? So we start off with 2 fruit flies, and they do whatever fruit flies do. And in 1 day, our population has grown to 6. It has tripled. A day later, it has tripled again, and now we have 18 fruit flies. And then it has tripled again, and now we have 54 fruit flies. Here we can see what this looks like on the graph. The points are plotted. There would be the graph of the fruit fly population. And notice as time goes by, that curve there gets steeper and steeper and steeper. Right? So an equation that would represent the population growth of the fruit flies here would be f of x equals 2 times 3 to the x. 2 is our starting population. It's like our A1 when we were looking at the geometric sequences. Right? It's what we started off with. 3 is b. It's our increase. It's the same as our ratio for the geometric sequence. And instead of having n minus 1, we're just going to have whatever the number of days is. Right? So x here is time. X is almost always time in these problems. Because we're looking at population growth or growth of something, maybe growth of money, something over time. So a function rule that describes the pattern above is f of x equals 2 times 3 to the x. This type of function in which the independent variable appears in an exponent is an exponential function. That's why it's called exponential function, right? Because your variable is the exponent. Notice that 2 is the starting population and 3 is the amount by which the population is multiplied by each day. Right? So if we follow our the formula I gave you in terms of setting up exponential functions, you'll know exactly how to write the equations. Right? You're looking for your starting population and you're looking for your rate of increase. Right? And if we're tripling, right, our rate of increase is going to be 3. So here we have, so remember that linear functions have constant differences. Exponential functions do not have constant differences, but they have constant ratios, right? Just like our geometric sequences, right? So each time we are multiplying by 3. So as the x values increase by a constant amount, the y values are multiplied by a constant amount as well. And this is our constant ratio, right? That's what we're going to be raising to a power. Right, so exponential growth occurs when some quantity regularly increases by a fixed percentage. The equation for an exponential relationship is given by y equals ab to the x power. So a is the initial value when x is 0, and b is our growth factor. So when no time goes by, we have to start with the population. Otherwise, it can't grow. This is just a little help for you in your calculator, just in case you have questions. So the caret symbol is generally used by most calculators and computers when evaluating exponents, and it means raised to the power. Right? So if I have 5 times 4 with a caret and then 3, that means 4 is raised to the third power, and then it multiplies by 5. Right? And the calculator will do that in the correct order. It will raise 4 to the third power first, right, and gives you 64, and then multiply by 5. It will not make a mistake and do it incorrectly and raise 20 to the third power, as students sometimes do. Right, the calculator knows the correct order of operations. If your exponent is a fraction, make sure to use parentheses. So the calculator knows it's supposed to raise 4 to the 1/2 power and not raise 4 to the first power and then go and divide by 2. Some calculators, the newer calculators, just bump the whole thing up and will know until you move it down again out of the exponent. It'll just put everything in the exponent and it will get it correct even without parentheses. But if you have an older calculator or if you have, one of the non-graphing calculators, you definitely have to make sure you put parentheses around that exponent. All right, so the calculator will raise 4 to the 1/2 power, which is the same as the square root of 4, which is 2 times 5, which is 10. Other symbols that might be on your calculator, it might be x to a box or x to the y. If I use my computer, I have x to the y. All right, and so just make sure when you have fractions that you put those in parentheses no matter what. All right, so just a little help with plugging into the calculator because we'll be evaluating some exponential functions. Like this one. So this one's in your notes. Let's evaluate some exponential functions. So the function f of x equals 500 times 1.035 to the x models the amount of money in a certificate of deposit after x years. How much money will there be in 6 years? Right? Well, so in this equation, x is time. So if I want to find how much there'll be after 6 years, all I have to do is replace the x with 6. And then I have to just make sure I raise 1.35 to the 6th power and then multiply by 5,000. You can just put it into the calculator just the way it's shown there because the calculator will use correct order of operations. So, and this is in your notes, by the way. So one thing you have to be able to do is evaluate exponential functions, which if you have a calculator isn't hard. And if you don't have a calculator, well, you're going to need a calculator because you're not going to want to do this. So 1.035 raised to the 6th power times 5,000. Now, I could have typed in 5,000, but I have a tendency to look at the base first. So it would be $6,146. This is money raised to the round to the nearest cent. So I have 276. That means it's going to be 28. That would round up. Right, so I'll just put 0.276, right, just so you can see, and that rounds up. So just round these to the nearest cent. Because nobody's going to give you a fraction of a cent anyway. That's an E. All right, let's look at the next one here. The function f of x is equal to 8 times 0.75 to the x, models the width of a photograph in inches after it has been reduced by 25% x times. All right, so notice that we're reducing by 25%. Which means the picture is maintaining 75% of its original size. Right? So we want what the picture keeps, what the picture is going to be. It's going to be 75% as large, not how much it lost. This one is also in your notes, so just add that because if you make your base, and later on we'll be writing equations, and if you make the base incorrect, well, everything you do with that equation is going to be incorrect. So the function f of x is equal to 8 times 0.75 to the x power is our equation, and we want to reduce it 3 times. All right, so in this case, x is number of times it's been reduced. Right, so we're going to make it 75% of its original size one time, and we're going to do that again, and we're going to do that again. And we don't have to calculate the first time and the second time and the third time we do it. All we have to do, since we have an equation, and it's an explicit equation, is to plug in 3 for x. And when we plug in 3 for the x and we evaluate it, we'll have the amount after 3 times. So there's no reason to find it for each one of these times. We just need it for the third time. All right, so 8 times 0.75 to the third power. All right, so I'm going to put that into a calculator. So I have 8 times and then 0.75 raised to the third power, and it's going to be 3.375 inches. Well, look at that. Why is the end-in value less than the starting size? Well, first of all, we were reducing the size. That's the first thing. But also, notice something about our base. So look at the base in the first problem. The first problem, that was 1.035, right? In the second problem, let's actually write that down. So here, B is 1.035. In the second problem, B is equal to 0.75. Do you notice something different about those bases? Right? Hopefully you notice that here, the base is greater than 1. And here, the base is between 0 and 1. I don't want to say the base is less than 1 because, well, -5 is less than 1 too, and we can't have bases that are negative. So our base here is between 0 and 1. So when our base is between 0 and 1, we have exponential decay. We'll learn more about that later in this lesson. So the second example is exponential decay. Right? We get smaller or we have less, we're losing money, something. The car is worth less, right? It's depreciating. And here we have exponential growth. So we'll talk about that more in a future lesson, but I wanted to introduce the two types of exponential equations. We can have growth or we can have decay. And what determines whether you're growth or decay is what your base is. Right? So here we got a lot out of these two problems. So make sure you get this in your notes. You can always pause so you can get everything down. right? And if my next slide is what's in next thing in your notes, which it is, I'm going to stop at this point. So I'm going to pick up in class with looking at equations for exponential growth and actually giving you word problems and writing equations to match those word problems. Thank you for watching both of these podcasts, and I hope you got a really good introduction here to exponential growth and decay. See you in class. Bye.